So, guys, now we're gonna be talking about the linear combination, so also the spanning sets, right? So, first, if we come to this, we're given this definition that in the last class we spoke about. They say that if we let x and y be two sets, and if all elements of x are also elements of y, then we say that x is a subset of y. So, the first definition that we come across, we saw that they say that if we let x and y be sets, all right, and all the element of this x are found in y, then this means that x is a subset of y. This is just some revision from set theory, right? What this means is that if y is equal to 3, 4, I don't know up until what, and x is equal to, it's containing some elements which are found in y, then this means that x is a subset of y. So now for this, we can go back and look at the definition of a linear combination. So for linear combination, we are saying that if we let V be a vector space and we take some collection of vectors to be a subset of V, you see, right? If we let V, if we come to linear combination, and we say here, let's say now let's say that we let V be a vector space. Let V be a vector space, and we take some vectors V1, V2, V3, let's just say up until Vn, because we don't know how many we can take, to be a subset of V. Alright, we're saying that if we let V be a vector space and we take some vectors, just that now we're choosing some unlimited vectors, or we don't know how many vectors we're choosing, right? That's what I'm saying, that up until n. If we let this be as a subset of V, here we can say that, we can say that a vector, V, which is an element of V, is called a linearly or a linear combination. Let me say linear combination if there exists, I think it should be a linear combination of Vi. You see right now? In this case, it depends how many of these are there. So I can just call this Vi for I equals to 0, 1, 2, up until n. Even here, I would have chosen that to be Vi, right? Which would have made sense. So I think I can also summarize this too. Let me say this. Let me say that if I let V be a vector space and I take Vi to be a subset of V, you say, right? And then I'm going to say that a vector V, which is an element of V, is called a linear combination of those vectors obviously I'm going to specify here that I'm talking about 0, 1, 2 up until n. All right. So we're saying that if we let V be a vector space and Vi to be some subset of V, meaning that we're taking more, we can take 1, 1, 2, and so on, right? So actually, I could even, let me just start it from 1, because obviously usually we don't have such a thing like V0. We always start from V1 and so on up until n. So we say that if we let V be a vector space and Vi be a subset of V, a vector V is an element of V if it's called a linear combination, and let me say a linear combination of those vectors. You say right now, if they exist there should exist some scalars. Also the scalars we're going to say I, such that I is equals to 1, 2 up until n, and this should be an element of R. This should strictly be taken from real numbers, such that V can be expressed in this manner. Let's say I say C1 V1 plus C2 V2 plus up until we get to Cn Vn. You see, right? So this is called a linear combination if it can be expressed in this manner. So now we are saying that, okay, let me do this. Now we're saying that if we know what a linear combination is, it means that we can look at a spanning of a vector. So now we can say this. Now we can say that if we come to spanning, let's now talk about spanning. We'll discuss more about linear combination or linear combination. But if we talk about linear combination, we're saying that a certain vector can be expressed in a linear combination of these vectors together with their scalars, right? If they exist, those scalars, element of real numbers. So we're saying now that if I talk about a span of vectors, let's now talk about a span of vectors. So when you come to a span of vectors, we can let's say now I just let some collection again. Remember we spoke about Vi. If we let some collection of Vi, in this case, we can just say this Vi, which is a subset. Or let me say Vi, which is a subset. Or let me say I equals 1, 2, so that we don't confuse this, right? Which is a subset of V. If I still take that collection of those vectors, which is a subset of V, then it will be that a span of those of Vi will be equals to, remember here, this is going also to include, this moves, Vi moves from 1 up until n. So remember I moves from 1 up until n, right? So I will be from 1 up until n. We see that we have some scalars and vector from 1 up until n, such that a scalar, remember, said that it should be an element of what? Of a real number. So if we say we take that or that collection of vectors, we say and that collection of vectors is a subset of V, then the span of those vectors will be equal to this. You see that we'll see whenever if we are asked to check if the span of this is equal to this, we'll be applying such an approach. So last we spoke about a few questions. We're gonna check how do we reply or how to answer questions, right? So let's say now we're given this, say let a be equals to 1 0 0 2, and they say b be equals to 0 1 0 1. And then they ask us they say determine if A and B are in span M1, M2. I think the question is somewhere here. If we check, let's see, the question should be somewhere here. Yeah, the question should be somewhere. Yeah, they say let A and B be this. And we determine if A and B are in the span of this. It's 1, 0, 0, 0 and 0, 1. This they say it's equals to span. This should be, so it's 1, 0, 0, 0, 0, 0, 0, 1. Yeah, or something like this. They say we should determine if this is the case, right? So for us to determine if A and B are in the span M1 and M2, we need to check. We need to check if A can be expressed in this format. Let's say I take some scalar 1 with M1 plus scalar 2 with M2. You see that? And also I need to check if B can be expressed in this manner also. You see that? So I need to check if they can both be expressed in that manner. So if we check now, for the first one, we see that A is equal to C1, and we're going to express it in a linear combination form. And we see that A is what? A is 1, 0, 0, 0, 2. This is equal to C1 is 1, 0, 0, 0. And I wanted to say plus here. C2. Oh, it's this one here, 0, 0, 0, 1. Right. So we should be able to put this in a linear combination form, right? So this will just be C1, 0, 0, 0 plus 0, 0, 0, C2. So this will be C1, 0, 0, C2. And after putting in that form, we should look for the scalars, the values of the scalars. You see, right? So if I look for the values of the scalars, C1 is going to be 1, and then C2 is going to be 2. Now, after getting this, I need to verify. I'm going to take this, plug and see if what I got is correct, right? So I'm going to come here, plug this. We need to verify if what we got is correct. Need to verify. Remember, our scalars, C1 is 1, C2 is 2. So if I put the 2 here and a 1 here, I'm going to get 1, 0, 0, 0, 0, 0, 2. And this will be equal to 1, 0, 0, 2, which is equal to this. You see right now. So if we see that this is the case, we can now say that hence A is in the span M1, M2. You see that. The nextly we can now try to express B. B is equal to C1, M1. Try to this thing is off. plus C2 M2. And then our B, let's see what our B is. Our B is 0, 1, 1. B is 0, 1, 1, 0. This was C1. This one was 1, 0, 0, 0 plus C2. This one was 0, 1. So this is going to be C1 0, 0, 0 plus 0, 0, 0 C2, and here we get C1 0, 0 C2. This side, remember, it's like this. So here we got that C1 is equal to 0, which is equal to C2. You see right now? Then now we need to verify. Now we need to verify, which is going to come and put this here. Remember here it was, we're only going to change this. We need to verify 0, 1, 1, 0. Then also we need to verify this. This was 0, 0, 0. This will be this will be 0, 0, 0, 0, which this is 0, 1, 1, 0. So when we check here, we realize that the two sides are not equal, right? So since the two sides are not equal, this simply means that it shows us that we can say, let me say, we can say, but let's just conclude instead of saying anything. We can say B is not in span M1, M2. You see right now? Then we can conclude with that. Now, looking at the second example, we can say this. Let's look at the second one that we have the. Let's see the second one. Yeah, the second one, they say we must show that into this, they say we must show, yeah. Let me just try to capture it. Just try to capture it. Now we can show that if we're given this px, right? Let's say show that px is equal to 7x squared plus 4x minus 3 is in span this, right? So now what we need to do, since we want to show that this one is found within this span, it means that we need to show that this can be written as a linear combination of this. You see right now. So it means that we are going to say here, we can say 7x squared plus 4x minus 3 is equals to, name this one C1, 4x squared plus x plus C2 into x squared minus 2x plus 3, which this will be for C1 x squared plus C1x plus C2x squared minus 2C2x plus 3C2. This 7x squared plus 4x minus 3, which this is equal to will be 4C1 plus C2x squared plus C1 minus 2C2x plus 3C2. This is 7x plus 4x minus 3. Remember, after expressing it in this format, we need to find C1 and C2. So this is how we can find C1 and C2. So now I'm going to equate, this is squared. I'm going to equate the like terms. X squared with x squared, 4x with 4x, constant with a constant. So in that case, or in that manner, we're going to say that 7 will be equals to 4 C1 plus C2. This can be like that. Then 4 will be equals to C1 minus 2 C2. That will be second equation. And minus 3 will be equals to 3C2, which this implies that C2 will be equals to minus 1. Right. This is equation 3. Then since we already know that C2 is equals to minus 1, we can now say that 7 is equals to 4 C1 minus 1, which this, if I take it to the other side, I'm going to get that this is 8 for C1. This implies that C1 is equals to 2. So if we try to plug 2 here, we are going to get minus 4. Let's see, 4 is equals to minus 1 minus 2. Let's see if we're going to get that. So what? Oh, this is minus 1. This is 2. 2 minus 1. Yeah, we confirm that, so that is correct. So we see that C1 is minus 1, C1 is 2, C2 is minus 1, right? We found those. And then if we can take them back, we can say, if I come and plug it here, then I plug it here, I find that this side is equal to this side. Then we can say that this is spinning, right? Or simply, someone would use augmented matrix. So for now here, let's just verify. We can just plug back and verify. So we can verify. When we verify, we can say that 7 x squared plus 4x minus 3 is equal to, remember our C1 is 2, then inside there it's 4x squared plus x, and then C is minus 1, then it's x squared minus 2x plus 3. This will be 8x squared plus 2x minus x squared plus 2x minus 3. 8 minus that is 7x squared, 2x plus 2x plus 4x minus 3. So we see that both sides are equal, right? Hence, px Yes, in span 4x squared plus x squared plus, is it minus 2x plus 3. You see, right? Then we can try to check how they did it, but most of the times, let's see what they'll say. We got that a is 2, b is minus 1, and they say that satisfies this system of equations. This means that we can write px as follows. You write like that, and then you verify. You see right now. Hence, px is in the given span. See? Then now let's look at this. We have this question now. They say let S be that, then they say show that S is a spanning set for P2. Let me take this question. And then we see now we're given this. They say let S be this and show that S is a spanning set for P2. We're not given P2 in this case. So it means that we need to come and let ax squared plus bx plus c be an element of P2 such that ax squared plus px plus c is equals to c1 x squared plus 1 plus c2 x minus 2 plus c3 2x squared minus x. And then now I need to solve for this, for the system. You see right now, so I can now do that. I can proceed and say this is c1 x squared plus 1 plus okay, I don't even need to put brackets. Let me just remove those brackets. The c1 x squared plus c1 plus c2x minus 2c2 plus 2c3 x squared minus c3 x. Then this will be c1 plus 2c3 x squared plus c2 minus c3 x plus c1 minus 2c2. This is ax squared plus bx plus c. So we realize that in this case we have to do the same thing, right? We have to equate this. We have to equate a being equals to c1 plus 2 c3. This is equation 1. And then we do the same thing. We take b equated to c2 minus c3, equation 2. Take c equated to c1 minus 2 c3. This is equation 3. We realize that this is not like the other questions. In this case, our a, b, c are unknown. Remember that time we had those. Now our a, b, c are unknown. So since our a, b, c are unknown, the best method to take here in this case would be for us to write this in a matrix augmented form. You see, right? Which this can be taken to this form. We can say, if we check here, we have c1, which that represents 1, but we don't have in the first equation, but we don't have c2, so that will be 0. c3 has the coefficient 2, we write 2, then you must put it in this form, right? Remember, this form is in the form of A, B, right? Given that this is going to generate our A, this is going to generate our B. So you must keep that in mind. So second equation, this is 0, we don't have C1. We have 1, we have minus 1. We have 1, we don't have C2 is 0, we have minus 2. This is A, B, C. You see, right? So we have something like this. Now, we need to now make this. We need to now have a leading 1, change anything below to 0, have a leading 1, everything to 0, have a leading 1. We have a 0, 0, 0. So we need to check for consistency. We need to check for unique solution. We said we have to check if this has a unique solution. If it does have a unique solution, then it means that this is indeed the spanning set for P2. You see right now. So now we're going to do that. We need to change this to a 0, so it means that we're going to write these ones 0, 2, 1, minus 1, AB. Then this will just be row 3 minus row 2. And then from here, we're going to have, now we have 0. Yeah, we need to change that to a leading 1 at the end. Then this will just going to be B. Then here we're going to have 0, 0, 1. Then this is going to be C minus A over minus 4. Then I multiply this row by negative 1 over 4. I'm sure you see this. Now, since we have this, it means that, let me see something here. See, the last one. Oh, the last one is C1 minus 2C2. This one I mistakenly wrote a mistake here, because I can see that we did these things last, but then I could see the problem. Let me see here. Yeah, this is fine. And then from here, it means that here I needed to change this to a 0 before I change anything here. It means that I need to say row 3 plus 2 row 2 minus 2 plus 2, 1 gives us a 0, which the formula means that it's correct. So that gives us a 0. This one will be minus 2, 2 minus 1. That is still minus 4, which is correct. And this one would be C minus A minus 2 plus 2B. Yeah, should be something like this. Let me see. Yeah. So from here, we need to change that to a leading 1, 0, 2, A, 0, 1, minus 1B. Then I need to change this to a leading 1. This is just going to be C minus A plus 2B over minus 4. And then let's change this to a 0, 0. Then I'll be 5. 0, 0, 0, 1, c minus a plus 2b over minus 4. First change this to a 0. 0, 2, I'm going to add row 3. A 0, 1. I'm going to subtract 2 row 3. So this is just going to be 0, 1, 0. Then if I add b with this, I'm just going to get b plus c minus a plus 2b over minus 4. And then this one is just going to be 1. It's just going to be 0, 0. And then here if I say row 1, which is a minus 2 into c minus a plus 2b over minus 4. Something like this, right? Then we realize that you can try to simplify this. Then we realize that indeed the system has a unique solution. So now I can deduce and say that the system has a unique solution, or is consistent. Has a unique solution. You said it. And in this case, we can tell that the solution will always exist for any of these values. Whether a becomes 0, 1, anything like that, the solution will always exist. We say right now. So we can say hence, as is seen, the span P2. So that was the question that we're checking, if S is spanning for P2. So now this would be the question for now. So I'm going to do another video where I go more into detail, touching more questions. So then the second questions that I'll be looking at, those ones are going to be focusing on the ones that use matrices the most, or the ones that come in this way. The ones that come, let's say maybe they give us, as they say, this is 1, 2, says 2, 3. They just give us anything of this man, you say right now. So we're going to be looking at such questions that come in this man, because these are the ones which are going to be used the most in basis. So we'll look at this the most.